To improve how autonomous language models write code and execute commands, developers routinely inject packaged markdown files, often called SKILL.md documents, directly into the agent's context window. This technique bypasses expensive parameter retraining and provides an immediate operational upgrade. We monitor aggregate benchmarks like SkillsBench, see the pass rates trend upward, and assume the system works. But treating skill utility as an empirical black box leaves severe blind spots. We track the output, but we lack a causal understanding of the mechanics inside the execution loop. A 2026 investigation by Jiang and colleagues provides that missing mechanistic layer. By normalizing over 8,000 trial records and running 528 controlled, matched triples, the researchers isolated exactly how agent performance diverges under different memory conditions. The findings dismantle three pervasive misconceptions in agent architecture: the assumption that skills function by injecting missing knowledge, the belief that raw execution logs naturally self-heal, and the assumption that high-precision retrieval is required for task success. Scaling reliable autonomous systems requires abandoning aggregate pass rate assumptions and studying exactly how representational formats dictate agent behavior at the trajectory level. The standard prompt engineering assumption is that agent skills act as technical encyclopedias. The intuition is that the model fails because it lacks specific domain knowledge or niche API parameters, and the skill document supplies those missing facts. This chart maps task completion drivers. Knowledge injection accounts for only 12% of successful runs. 81.3% of the time, the skill acts as a procedural anchor. It operates like a strict flight checklist, enforcing execution sequencing, dependency validation, and deterministic testing protocols. Frontier models like GPT 5.3 Codex and Gemini 3.1 Pro already possess the latent knowledge required to write Python scripts and Unix commands. Their actual point of failure is stochastic drift. They execute steps out of order, mismanage background processes, and lose execution discipline over long horizons. Fixing agent reliability is a problem of procedural enforcement. Structuring a skill to govern behavior yields far higher task completion than trying to teach the model new concepts. The tool execution sandbox is a highly chaotic environment. In raw baseline executions, agents routinely crash due to uninstalled packages, missing background daemons, incorrect system paths, and corrupted bash syntax. This chart visualizes execution breakdowns. By establishing strict prerequisites, skills wipe out infrastructure failures, dropping from 5.3% in raw baselines to 0.2%. Output format errors follow the same trajectory. Procedural anchors cut mismatches by half, dropping from 7.4 to 3.2%. A persistent LLM pathology occurs when agents write code, inspect it visually, and confidently declare the task complete, without ever actually running the test suite. This static verification trap guarantees high failure rates downstream. Because the skill document contains mandatory runtime verification steps, the agent is forced to trigger specific system tests, evaluate the exit codes, and correct any failures before terminating the loop. Standardized bash contracts and explicit verifiers effectively eliminate low-level tactical breakdowns in the execution layer. When engineers design memory systems, they usually choose between two representational formats: workflow memory, which is a linearized summary of chronological actions, and highly distilled modular skills. Workflow memory contains an inherent flaw: procedural residue. It summarizes past attempts chronologically, preserving exploratory dead ends, trial and error commands, and abandoned debugging loops. When the agent reads this residue, it blindly repeats past cycles, burning the budget and resulting in a 10.6% timeout rate. Distilled modular skills strip away residue entirely, establishing a token-efficient command sequence. But modularity introduces a cognitive tax. Lacking contextual history, the agent frequently executes the procedure even when preconditions do not match. This blind forcing causes guidance misapplication in exactly 10% of runs. Upgrading memory from raw workflows to passaged skills trades one pathology for another. It stabilizes the sandbox execution layer, but shifts the primary point of failure to contextual invocation. Advanced agent architectures like Voyager and Memel Harness employ recursive pipelines, generating new procedural skills by analyzing their own past trajectory logs. This assumes the large language model running the synthesizer can look at a mixed pool of successful and failed attempts, separate the noise, and independently deduce the correct steps. This graph maps downstream success across trajectory mixtures. With explicit success and failure labels, performance remains stable even when failed traces dominate the pool. But under the no-hint condition, where labels are withheld, downstream performance plummets from 74.6% to 40%. Without explicit outcome tags, the model cannot reliably distinguish a valid procedure from a dead-end syntax error. The synthesizer actively treats failed explorations as normative steps, embedding broken logic and invalid flags directly into standard operating workflows. Unverified experience does not self-filter. If an agent pipeline synthesizes unannotated trajectory logs, it will permanently codify its own failures into its skill library. As an agent's memory bank scales from dozens of skills to hundreds, retrieval becomes the obvious bottleneck. Standard engineering practice treats top-1 semantic precision as the definitive metric for task success. To test this, researchers designed a 3-arm diagnostic, scaling the candidate pool up to 100 skills, and injecting highly confusing, semantically similar distractors into the environment. During live execution, as the candidate pool expands to 100 options, the agent's ability to select the exact ground truth skill collapses from 29.6% to 3.3%. Yet downstream task success holds steady at 39.3%. The agent solves the task without the perfect skill. This occurs because interactive agents do not make a single hard selection. During execution, they maintain multi-candidate recall rates between 54 and 74%, actively scanning multiple files in their working context. Furthermore, semantically related distractor skills share structural invariance. A skill for configuring a background web server contains the exact same dependency checks and daemon management commands as the skill for an asynchronous task queue. The distractor provides a valid procedural template. Exact one-to-one precision is neither necessary nor sufficient. Providing broad recall of related structural templates is the actual mechanism driving execution success. Isolating these operational mechanics yields strict architectural principles for anyone building production agent environments. First, format skills as strict verification contracts. Strip away narrative tutorials and rely strictly on standard POSIX bash primitives rather than proprietary framework wrappers. A skill built in OpenAI Codex achieves up to 30 percentage point gains when transferred directly into Google Gemini's command line interface, provided the bash commands are universal. Second, mandate dual-channel synthesis. All memory distillation engines must use explicit verifier tags to separate positive procedural steps from negative failure warnings. Third, defeat semantic confusability via dual-tier retrieval. Vector databases should index hard environmental preconditions and tool dependencies, not generic task descriptions, to ensure the agent receives the correct structural template. Finally, eliminate invocation misapplication by implementing dynamic lazy loading. Inject only metadata and preconditions into the primary context, forcing the agent to deliberately invoke a tool to load the full procedural body. Applying these structural rules moves agent development away from fragile prompt heuristics and roots it firmly in deterministic systems engineering. The data requires a shift in how we approach autonomous LLMs. We must stop assuming we need to teach the model what to do and build infrastructure that strictly enforces how the model does it. Resolving stochastic output requires standardizing strict execution contracts, mandating runtime verification, and filtering memory through explicit outcome labels. Demystifying agent skills provides the empirical roadmap for engineering the next generation of highly reliable, enterprise-grade autonomous software systems.